Welcome to this explainer. Whether you're an engineering student deep into finals prep or a seasoned pro brushing up on the fundamentals, you are in exactly the right place. Today, we're serving up the ultimate high-yield electrical engineer's study guide for mastering electrical networks. We're going to strip away all that dense textbook jargon and just get straight to the visual concepts that demystify what's actually happening inside your devices. Okay, let's dive into our structural roadmap. 1. The blueprint. 2. Building blocks. 3. The interview trap. 4. Governing laws. 5. Real-world applications. And finally, 6. The perfect answer.
Section 1. The blueprint.
So let's say you're sitting right across from a professor or maybe a hiring manager, and they hit you with this question. What exactly is an electrical network? Sounds pretty simple, right? Well, the magic word you need to remember here is interconnection. Because think about it, you could have 3 resistors, a capacitor, and a voltage source just sitting loosely on your lab desk. That's a pile of parts, not a network. It's only when they're actually wired together to provide paths for current to interact that they become a true interconnected system. And this brilliantly illustrates the concept using something we interact with literally every single day, your home's water plumbing. It's the perfect mapping. That water tank supplying the house, that's your voltage source. The water pressure actually pushing the water, that's your voltage. The flow of the water itself is your electric current, and the pipes carrying it are your wires or conductors. Got a narrow pipe restricting that flow? Boom, that's resistance. And wherever those pipes branch off or meet up, that is an electrical node. Just like water flows through pipes, electric current flows through an interconnected system of components. Section 2. Building blocks. Now, a network can contain a bunch of different elements, but let's quickly run through the 5 heavy hitters. First up, the resistor. It acts like a bottleneck, opposing the current and turning electrical energy mostly into heat, which is dictated by good old V equals IR. Next, the capacitor. Super important for filters and timing because it temporarily stores energy in an electric field. That's I equals C dV dt. Then the inductor, doing something similar but storing energy in a magnetic field, where V equals L di dt. And finally, our active elements that actually bring the system to life. The voltage source, maintaining a specific voltage, and the current source, maintaining a specific current. Remember, as amazing as these individual pieces are, they do absolutely nothing until they're linked together. Section 3. The interview trap. All right, pay super close attention here, because this is a classic high-stakes technical interview question that catches so many people off guard. You'll hear the terms electrical network and electrical circuit thrown around interchangeably all the time in casual conversation. But in classical network theory, there's a really vital distinction. A network is simply an interconnection of electrical elements. Period. It doesn't even need a closed path. But a circuit? A circuit is generally a network that actually contains at least one closed path where current can flow. So the crucial point to remember is this easy rule of thumb. Every circuit can be viewed as a network, but not every network is necessarily a circuit. Imagine 2 resistors connected in a straight line, but not looping back to a source. You've got a network, sure, but you don't have a circuit. Now, quick caveat here, some textbooks do use the terms anonymously, so always read the room and know your professor's preference, but bringing up this classical distinction, that shows a really deep foundational grasp of the theory. Section 4. Governing laws. Once you wire these components up, everything starts with Ohm's law, V equals IR. Connect a battery to a resistor, and that battery creates a potential difference, an electric field in the path. The resistor then decides just how much current gets through. It's a direct, literal relationship. Crank up the voltage, current goes up. Crank up the resistance, current goes down. This is absolutely the bedrock of all network analysis. Now, what's really fascinating is how this maps perfectly back to our water analogy. Kirchhoff's current law, or KCL, tells us that at any node, the total current entering must equal the total current leaving. Think back to that pipe junction. If 5 liters of water flow into a junction every minute, exactly 5 liters gotta flow out. Maybe it all rushes down one pipe, or maybe it splits into 2 liters here and 3 liters there. Electric current behaves the exact same way at an electrical node. No charge just vanishes. It simply takes different paths. And complementing KCL is Kirchhoff's voltage law, or KVL. This one states that around any closed loop, the algebraic sum of all voltage rises and drops is exactly 0. Let's say your source provides a 10-volt rise. As that current travels through the loop and hits a resistor, there's a 10-volt drop. Plus 10 minus 10 equals 0. Energy is perfectly conserved all the way around the loop. To help build your intuition for how current navigates all these nodes and loops, here's another awesome mental model. Think of a city road network. The roads are your wires. The traffic? That's your electric current. A lane closure causing a huge backup is your resistance. Intersections where cars can turn are your nodes, and a full driving route is your electrical loop. When you're analyzing a complex network, you're basically acting as an enthusiastic urban planner, calculating exactly where traffic will bottleneck and how much pressure or voltage is needed to push those cars along.
Section 5. Real-world applications. So why go through all this textbook theory anyway? Let's move to the system level and see how this builds from isolated parts into actual, tangible hardware. Engineering is all about layers. You start with isolated electrical elements. You wire them up. That's interconnection. Boom, you have an electrical network. Then you apply circuit analysis to figure out the voltages and currents. And ultimately, that fully analyzed network becomes a complex working electrical system.
And you see this progression everywhere, across wildly different scales. Take that standard mobile charger plugged into your wall. It takes AC mains, rectifies it, filters it, steps it down, and pumps out a clean DC voltage. All those macro sections, just interconnected electrical networks. But then zoom way, way down to the microscopic level. If you're looking at VLSI, very large-scale integration, a single transistor amplifier inside your smartphone's processor is also an electrical network. It's got a tiny transistor, a tiny resistor, supply, and ground. You use the exact same network analysis to figure out the gain and power consumption of that microscopic chip as you do for the charger on your wall. It's the exact same fundamental concept, just applied across completely different scales.
Section 6. The perfect answer.
All right, it's time to pull everything we've talked about today into one perfect package. If you ever need to define this concept on an exam or in a job interview, this is your absolute mic drop answer. An electrical network is an interconnection of electrical elements, such as resistors, capacitors, inductors, voltage sources, current sources, and other electrical devices connected through conducting paths. The network provides relationships between electrical quantities such as voltage and current, and we analyze these relationships using fundamental laws such as Ohm's law and Kirchhoff's laws. Seriously, memorize that. It hits the components, the crucial element of interconnection, the very purpose of the network, and the governing math. So now that you know the exact rules and blueprints that govern the invisible forces powering our entire technological world, what kind of network are you going to build next?